The acceleration of an object is directly proportional to the unbalanced external force acting on the object and inversely proportional to the mass of the object. The acceleration of the object is in the same direction as the unbalanced external force. Forces produce accelerations. Accelerations do not produce forces. The forces on the boy in the red shirt are balanced, hence he doesn't slide. Frictional forces are static in this situation. The forces on the yellow-shirted boy could be balanced and he would be sliding down at a constant velocity rate, or they could be unbalanced and he could be accelerating down the slide. Either way, the amount of frictional force will help determine the net force and whether or not the boys actually change their state of motion. In the expression on the previous slide, m represents the mass of the object experiencing the acceleration, and F represents force. Force, a push or pull, any influence that causes an object to change its velocity. The unit of force is the unit of mass times the unit of acceleration, and is measured in newtons. 1 newton is the force required to give a 1.0 kilogram object an acceleration of 1.0 meters per second squared. Newton's second law is also referred to as the law of acceleration. If object A exerts a force on object B, then object B exerts a force on A, which is equal in magnitude and opposite in direction. It is important to remember that the forces in the action-reaction pair mentioned act on different objects. Newton's third law is also called the law of interaction. Remember, it is always the same amount of force, but sometimes the results are different. The results are the effect which was caused by the force on each individual piece on the force pair. Hence, if the masses are different, like in a small car and a large truck, then the effect can be different, even though the forces are on equal magnitude. Newton's third law tells us that forces always come in pairs and that the forces in each pair are of equal magnitude, are opposite in direction, and act on different objects. You can never have a single force without a counterpart somewhere in the universe. What are the force pairs that are involved in each of these situations? There is one more important piece to the dynamic and static model. It is called Newton's third law. Forces come in pairs. Understanding Newton's third law, we can ignore internal forces and then only search for external forces acting on the object. Take a moment to read this cartoon, then take a minute to study this image. What happens if the green-shirted man decides not to pull back on the rope? For example, with the palm of your hand, push on a book, desk, or table. You are exerting a force on the object you are pushing. At the same time, you can feel a force on your hand. There seems to be two forces, the one your hand exerted on the object, and another force on your hand. What is the relationship between these forces? Imagine that you hold the two force probes, one probe in each hand. You will notice that each force probe has a hook on it. Connect the two force probes together and pull as seen in this figure. You can experimentally do this by connecting your fingers together with somebody else. Try having them pull on you without pulling back. What happens if somebody doesn't resist the effort force of pulling? Why does it seem that a bug hits a windshield with more force than the windshield hits the bug? The effect on the bug is worse than the effect on the windshield, but the force is still the same. Forces come in pairs. An example would be the weight and normal force pairs in the figure. The weight of an object and normal force are sometimes equal, but they are not force pairs. For good reason, many people think of mass and weight as the same thing. It is difficult to distinguish between the two if your experience is restricted to one location on the Earth. Mass and weight, however, are not the same. Mass is the quantification of an object inertia. That is, mass is a measure of an object's resistance to change in state of motion. Weight is a force. Weight is the force of attraction toward the Earth. Mass is a scalar. Weight, or force, is a vector. Suppose we hopped a shuttle and went to a remote area in space where there was nothing around. Since we are in empty space, we would all be weightless. Even a 50-pound cannonball we brought with us would be weightless. Now let's put the cannonball into a cannon and fire it at 100 miles per hour. So we need a volunteer to stand directly in front of the cannon and catch the weightless cannonball. What? No takers? Well, you are wise not to stand in front of the cannon. The cannonball is still going to resist a change in state of velocity just the same as if it were on the Earth. The cannonball still has inertia, or mass, even though it has no weight. What if we just put you in the cannon and allowed you to be shot out? Hopefully this example helps you start to see that there is a difference between mass and weight. We will explore mass and weight in more detail as we go through this and the next lesson. It is much easier to lift these masses on the moon where the weight is less than the weight on the Earth. However, in a mass lifting contest, the value of the mass at either location would be the same. We move from a virtual field trip to a thought experiment in the next page. You'll be asked to take some time and think about the question posed, as it is quite complex. A class of 50 students will generally spend between 5 to 10 minutes stating wrong answers to the question before someone stumbles upon the correct answer. It is important for you to go through the same thinking process. A person stands on a skateboard and pushes against the wall. The wall pushes back on the person and the skateboard moves or accelerates. According to Newton's third law, the force exerted by the person on the wall and the force exerted by the wall on the person add to zero. If these two forces add to zero, why is it that the skateboard accelerates? A free body diagram differs from your picture of the problem. In a FBD, you isolate the object that you are interested in by drawing it as a single point. Then draw on this isolated object only those forces that act directly on the object. Do not include forces that the isolated object exerts. Also, include your sign convention in the FBD. A well-drawn FBD is crucial to the successful solution of a problem involving Newton's laws of motion. The reason for you going through the skateboard problem was to illustrate the importance of the FBD. When you consider only the forces acting directly on the skateboarder, the force provided by the wall is the only external force acting on the skateboarder. Since there is an unbalanced external force acting on the skateboarder will accelerate according to Newton's second law of motion. A car is traveling at a constant velocity straight ahead on a flat, frictionless road. On your own, draw a free body diagram for the car. The driver in this car fires retro rockets so that the car is de-accelerating while traveling on a straight, flat, and frictionless road. On your own, describe the free body diagram of the car. The previous two situations had a force exerted by a surface on an object. A surface will always push on an object in a direction that is perpendicular or normal to the surface. Such a force exerted by a surface is called a normal force. A 4-kilogram object is pulled along a frictionless surface to the right by a 6-Newton force. How long does it take the object to travel a distance of 25 meters, assuming the object starts at rest? You can use kinematics or dynamics equations to solve this example. A 4-kilogram object is pulled along a frictionless surface to the right by a 6-Newton force directed 30 degrees above the horizontal. How long does it take the object to travel a distance of 25 meters, assuming the object starts at rest? You must remember that the force needed is in the direction that the box will move. You can use the x component of the force, aka multiply this force by the cosine of 30 degrees, and then repeat the process from the previous example. An 85-kilogram person stands on a scale that reads weight in newtons while standing in an elevator. What is the reading on the scale when the elevator stopped? The forces are balanced, therefore weight would be 85 kilograms times 9.8 meters per second, or approximately 850 newtons. Note the weight down would equal the normal force supplied by the spring scale. Hence, if the elevator is stopped, the reading would be exactly equal to the person's weight. What if the elevator is accelerating upward at 3.5 meters per second squared? With the elevator accelerating upward, the force supplied as the normal, which would be the reading that the scale would show, would be a combination of the acceleration due to gravity and the acceleration of the elevator upward, 9.8 meters per second squared and 3.5 meters per second squared. This is 13.3 meters per second squared, and you would have to multiply this time the mass of the person riding the elevator. The scale would read 1130.5 newtons. An 85-kilogram person stands on a scale that reads weight in newtons while standing in an elevator. What is the reading on the scale when the elevator is moving upward at a constant speed of 5 meters per second? What does constant speed imply? The answer is balanced force. Therefore, the weight would be the same as if the object was stationary. The weight would be approximately 850 newtons. Remember, a correctly drawn free body diagram is essential to solve problems involving Newton's laws of motion. Newton's laws of motion are useful in a wide variety of situations, ranging from the motion of a baseball when struck by a bat to the motion of the planets in the solar system. This wide range of applicability is why Newton's laws are so highly regarded. In this lesson, you covered the following objectives.